We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello, my name is Professor Gautam Dihora. I'm Assistant Professor in Civil Engineering Department at Shantilal Engineering College, Bhavnagar. So I'm uploading this video for students of 6th semester Civil Engineering Department because all our academic activities has been suspended due to lockdown because of the coronavirus. So first we'll see important with water engineering regarding collection and conveyance of water. So this is the list of topic that we are going to cover in this video in collection and conveyance of water. First is the intake, then location of intake, then some design consideration and design of pump and rising main. So if we consider or if we talk about collections of water and transmission of water, then collection means collection of water from surface or either subsurface sources. So we know all about the sources from which we can get water. So first of all, we have to understand what is the water supply scheme. So there are 4 components under the water supply scheme. First is the collection work, and second the transmission work, third is the purification, and fourth distribution work. So collection of works, that means we have to provide some structure in the source, at the source from where we can withdraw the water. And that structure is known as intake structure because we are taking the water. That's why it's called intake structure. So as you can see in this collection work, one structure here, there is one structure is located here in this reservoir, which is called intake. And from this intake we are supplying our water to water treatment plant or either water treatment plant or to the city, right? So from this intake we are pumping the water through this pipeline, which is also known as transmission work or rising main. We call it rising main because the elevations of the ground is rising. That's why it may also call rising main. So from the intake, we are supplying the water, we are transmitting the water up to the water treatment plant. Here you can see one treatment plant. Here there is one intake. So from intake, we are supplying water to treatment plant, and from the treatment plant, we are supplying it to the distribution network. We will talk about water treatment plant later on and distribution network also in the later on. So basically intake or intake structure which is provided to withdraw the water from the source. Right? So the raw water intake structure are used to withdraw water from the source, and the primary purpose of intake is to selectively withdraw best quality water while excluding fish, floating debris, coarse sediments, and other objectionable suspended matter. Right. So intake should be provided where the quality of water is good and in all season the water is available, as well as we have to see that no other floating or objectionable material enter in the intake. So that's why we are providing screen in the intake only. So in water treatment plant or water supply scheme, the screens are provided at the intake itself. If we talk about the surface water intake classification, then it can be classified under the 3 category. First is according to type of source, That means a river, canal, reservoir, or lake. So if we are providing intake in a river, then it is called river intake. If we are providing intake in a canal, then canal intake. Same way reservoir intake and lake intake. And according to position of intake, so intake may be either submerged intake or exposed intake. And according to presence of water in the intake tower, so if the water is present, then wet intake, and if it is absent, then dry intake. This photograph show the floating intake. So the floating intake is provided above the platform, as you can see in this photograph. About this floating intake, pumps are provided, and from here the water is withdrawn. So this intake is generally provided for temporary purpose. That means we have to provide water for a few months or for few weeks or for certain period in a year, then only this kind of floating intakes are provided. This is called exposed or tower intake, and this kind of intakes you may have seen in reservoir or river. Many times you may have seen or noticed this kind of tower in reservoir. So this is exposed or tower intake. So this intake structure is generally used for large projects on river or reservoirs with large water level fluctuation. We know that the water level fluctuations will be there in reservoir and the river, right? So when this kind of fluctuations is there, then we are providing this kind of exposed or tower intake. So basically here we are providing gate control opening, which are generally provided at several levels in order to permit selection of best quality water. So in this intake, gates are provided at different level inside the reservoir or inside this intake, or say if it is provided in the river, then in the river intake, right? So that we can withdraw selectively the best quality of water from the intake. This may be wet intake towers or dry intake tower. These are certain design consideration for the intake. So this intake should be sufficiently heavy, right? We know that we are providing intake in water, so that uplift pressures of water will be there. Water will exert uplift pressure on the intake. So it should be sufficiently heavy so that it may not start floating due to the upthrust of water. And also it should be heavy so that it will not be washed away by heavy water currents during the floods. All the processes which are expected to work on intake should be carefully analyzed, and intake should be designed to withstand all these forces. Its own weight, then uplift pressures, then forces due to heavy currents. These all forces has to be considered while designing of intake. And the foundation of the intake should be taken sufficiently deep, right? If it is not taken sufficiently deep, then this intake may overturn, right? So to avoid the overturning of the structure, sufficient depth of the foundation should be provided. Intake should be constructed in a, it should not be constructed in a navigation channel, right, as far as possible. And if it has to be constructed in navigation channel, then a cluster of piles should be provided all around the intake to protect it because of the forces which is caused by moving ships and steamers. As we have discussed that we are providing strainers, or we can say screens, in form of wire mesh, right, at the intake only. This will protect, or this will avoid entry of large floating objects and fishes into the intake. And this intake should of such size and so located that sufficient quantity of water can be obtained from the intake in all circumstances. So that intake should we should be obtaining water during the dry period also. So the location should be provided in a such a way that during the driest period of the year, sufficient quantity of water is always available. So, this where we should provide the intake, or how we can select the site or the location of the intake. So first, it should be very nearer to the treatment plant, right? If it is far from the treatment plant, then we have to pump the water from for further distance, and the energy cost for the pumping cost will be more, and also the pipeline cost will be more. So it should be nearer to the treatment plant. Then it must be located in the purer zone of the source, because we know that the many cities are discharging their wastewater in the nearby river, right? So that it should not be located on the downstream or in the vicinity of the point of disposal of wastewater. The site of the intake should be able to fulfill water demand at peak levels, right? So it should permit greater withdrawal of water if required at a future date, as well as we should be able to withdraw the water even during the driest period of the year. It should be safe from the flood, right? The site should remain easily accessible during the floods. So intake should not be submerged during the floods. It should remain accessible during the flood also. So the height of the intake should be considered by checking the HFL or high flood level in the reservoir, or we can say in the river. The flood water should not be concentrated in the vicinity of intake, and it should not interfere with river traffic if we are providing in a river. So that was about the collection part. We are collecting water from the intake, and then uh, next part is the transmission part, or conveyance of water. So there are two stages in transportation of water. In first, we are transporting water from the source to the treatment plant, and second, conveyance of treated water from treatment plant to distribution system. We will talk about the conveyance of water from treatment plant to distribution system later on, but first we'll concentrate on the conveyance of water from source to treatment plant. So we can supply the water from source to treatment plant by two way, either free flow or pressure conduits. The free flow, that means through gravity, and second one is the pressure conduit. So first we'll see the free flow conduits. So in this system, the surface of water in the conveying section flows freely due to gravity. Right? There is no pressure. We are not pumping the water. And the conveyance conduits must follow the hydraulic gradient. Example are canal, flumes, gravity aqueduct, tunnel, etc. But there are certain drawback of free flow system also. Though we are not pumping the water, there is no energy consumption, but there are certain drawback, like very long transporting section is required, and water is lost by percolation and evaporation, right? If we are providing or supplying water through canal, and there may be percolation and evaporation of the water, then water will lost. And there is the possibility of pollution from surface drainage, because the canal from nearby fields, pollutions from surface drainage may enter. Head loss due to friction is considerable in open flow or free flow conduits, and construction as well as maintenance costs are also high. So in pressure conduits, as the name suggests, in this system the flow in conduits is under pressure. For example, pressure aqueduct, pressure tunnel, pressure mains, etc. Then for the design of hydraulic design of the conduit, we have to see certain parameters. Like the design of supply conduit, it depends on resistance to flow, that is frictional resistance. This depends on the smoothness or roughness of the pipe. If the pipe surface is rough, then the frictional losses will be more, and if the pipe surface is smooth, then frictional losses will be less. Second one is available pressure or head. What is the head or pressure available at the source? Say if our source is located at higher elevation and water treatment plant is located at lower elevation than the source, then gravity flow is possible. But if the source is located at lower elevation and water treatment plant is located at higher elevation, then we have to pump the water. Third one is allowable velocities of the flow. Now we cannot provide more velocity in the pipeline, especially in the pressure conduit, because the frictional losses will increase in the pipeline if the velocity is increasing. So there are certain guidelines also provided in CPHEO manual on water supply and treatment for the allowable velocities. Then third one is the scour. This cover happen if the velocities are more, right? If the more velocities are there, the turbulent flow is there, then the scour of the inside surface will be there, and the frictional losses then it will increase. Then sediment transport. We know that it also depends on the velocities. If the velocity is too low, then the sediments or the particles are there in raw water will settle inside the pipeline, right? This should not happen, right? So in the pumping system we should maintain some minimum velocities like 1 meter per second, right? So that uh, the sediments are not settle inside the pipeline and it is transported along with the water. Next one is the quality of water. What kind of quality of water either we are providing, or we are supplying raw water, or we are supplying treated water, or we are supplying sewage. And then relative cost. So generally, we are using Hazen-Williams formula for pressure conduits and Manning's formula for free flow conduits. Right. So this is Hazen-Williams formula, and which is used for pressure conduits. V is equal to 0.849 C into R raised to 0.63 into S raised to 0.54. And for circular conduits, the expression becomes V is equal to 4.567 into 10 raised to minus 3 C into D raised to 0.63 into S raised to 0.54. And Q is equal to 1.292 into 10 raised to minus 5 C into D raised to 2.63 into S raised to 0.54, where V is velocity in meter per second, S is slope, R is hydraulic radius, which is A by P. So for circular conduits, this hydraulic radius or R will be D by 4. C is Hazen-Williams coefficient and Q is discharge. And for free flow conduits, we are using Manning's formula, which states V is equal to 1 by N into R is to 2 by 3 into S raised to 1 by 2. And N is Manning's coefficient of roughness. So for pipe flow, another formula which we are using is Darcy-Weisbach formula. This formula is used to calculate the head loss in the pipe, which state S is equal to FLV square divided by 2GD. H is head loss in meter, D is pipe diameter, V is velocity, L is the length of pipe in meter, F is friction factor, which is dimensionless, and G is acceleration due to gravity. So here in CPH EO manual on water supply and treatment, the Hazen-Williams coefficients are given for different pipe material like for cast iron, mild steel, galvanized iron, and for new pipes and for design purpose, what should be the C value or recommended C value that is given in CPHEO manual. So you can refer the CPHEO manual for recommended C value for new pipe as well as for design purpose. So here you can see that for design purpose C value is lower uh, than the new pipe, right? So because of this, we will have more frictional, we can say frictional losses obtained for the design purpose will be more, right? Because the C value is lesser compared to new pipe, right? So as the C value is higher, the losses will be less. These are the Manning's coefficient of roughness as per the CPHEO manual. So for different types like masonry, stonework, or steel, cast iron, ductile iron, pipeline or unlined, and cement mortar lining. What are the N values? This is also given in CPHEO manual. And these are the friction factors in Darcy-Weisbach formula as per CPHEO manual for RCC pipe, AC pipe, CI pipe. And for different diameters, these are the friction factor that we have to consider. Then comes the losses on pipes, like when we are supplying water through pipe, then there will be losses in the pipe, right? This is not the water losses, but there are two kinds of losses in pipe, which is major losses and minor losses. And these losses are due to the friction and obstruction. Right, it is not water losses, but these losses are due to the friction and obstructions in the pipe. So total losses or HL will be equal to major losses plus minor losses. So this major losses is known as pressure losses or head loss due to friction, right? Now this friction, head loss due to friction is depends on, as I told you, this depends on the smoothness or roughness of the pipe. If the pipe surface is rough, frictional losses will be more. If the pipe surface is smooth, then frictional losses will be less. So in newer pipe, frictional losses will be less compared to old pipe. This Darcy-Weisbach formula is used to calculate head loss for pipe 4, and this already we have discussed. And using this, we can calculate major losses, which is frictional losses. Now other losses will be also there in the pipeline. These will be because of sudden expansion in the pipe or sudden contraction in the pipe or bend in the pipe or pipe fittings like valves, elbows, etc. Then obstruction in the pipe, right? These are the minor losses. These minor losses can be calculated using the equation kV square divided by 2G. K is the constant and its value is given in the manual, CPHEO manual. So K value is different for different section, like for elbow 90 degree it's from 0.5 to 1, for 45 degree 0.4 to 0.75. So for different angle the values are different. V is the velocity and G is gravitational acceleration. So using this we can calculate minor losses in pipe for each band or for each type of fittings. We can calculate minor losses. So if we add these minor losses and major losses, then we will have the total head loss in the pipe.